What is a direction? So we've been talking about vectors, like the vectors shown here, and we know that a vector is a quantity that has both a magnitude and a direction. But what exactly is a direction? This can really get confusing when you think about how you could have something like a price vector or a revenue vector that has a direction. So how could a price or revenue have a direction? What exactly is a direction? Well, let's go back to the pure fundamentals and think about before algebra or linear algebra ever existed. Okay, but what did exist at that time and still today was coordinate systems. So what exactly at its most fundamental is a coordinate system? A coordinate system is just a tool that we use to map out locations in space, points in space. That's it. You can have a one-dimensional, two-dimensional, or three-dimensional coordinate system. You could think about a one-dimensional coordinate system being for something like a conveyor belt. So the coordinate system is just along a line. But a one-dimensional coordinate system doesn't have to be along a line. It can be in any one-dimensional case. Maybe you're mapping out points along some path like this. What you do is you just put some scale, some gradation along the path. So this is 1, 2, 3, 4. And maybe you have a negative direction as well. This is the origin. And so with that, if you specify any real number, then what that's giving is the location of a point along this path relative to the origin. But you could obviously do this along a line as well. That's what we most typically think of as a one-dimensional coordinate system. The tick marks of the scale most commonly are evenly spaced, but you can space them however you want. But the main idea is, since this is one-dimensional, then to specify a location relative to the chosen origin point, you just need one parameter. So it's important that we clearly understand what a dimension is. So this is one-dimensional. We have three-dimensional space. What exactly does that mean? What are we talking about? This term dimension. Well, the idea is, if you think about, say you were a caveman or a cave woman, you just woke up one day, you were here, walked outside, one of the first people on Earth. Well, there would be all of these different phenomena around you. Hot and cold, weight of objects, things would be being pulled towards the ground to different extents. Time, so you notice that there's like duration, there's things before, at present, and after. And also like space around you. Different objects have different spans. There's different locations around you. But space is unique from the other phenomena in the sense that to describe the time of something, you have some system you're working on and you want to track the time, well, you only need one parameter. Time is one-dimensional. There's a before, there's an at present, there's an after. That's it. You can think about mapping time on a line like this. You just need one parameter. Same idea with weight and temperature. But space around you is different in that if you had some system, like you're in a room or something, and you want to map out the location of any point in that entire room, you're going to have to use three parameters. There's no other way around it. You have to. Now, what exactly you choose those parameters to be is up to you. This shows like the most popular case of axes at right angles to one another, but you could do anything. You could have one parameter based on a path like this, another parameter based on a path like this, whatever. But no matter what method you choose, you're going to have three parameters, no matter what. And each of those parameters are referred to as a dimension, which is why space in general is three-dimensional. Okay, so we understand what exactly a dimension is. Let's come back to coordinate systems. So mapping out points in space. Let's forget about time, temperature, weight. Let's come back to coordinate systems. So in terms of a coordinate system, what exactly is a direction? Because the term direction, yes, you could think about direction in terms of time, something like that. But at its most fundamental, the term direction is related to space around us, right? And so, okay, in that sense, what exactly is a direction? Let's think about this question from the perspective of 3D space. So imagine we have some system, we're in a room or something, we decide on an origin point right here, and we can map out all points in this space with whatever coordinate system we want. The most common type of coordinate system is a rectangular coordinate system where you have these straight line axes for each of the 3 dimensions, and they're all perpendicular to one another. That's the most common type of coordinate system. You have the X, Y, and Z axis. But there's other types of coordinate systems. You have cylindrical coordinate systems, where the 3 parameters are, you specify a radial distance from the origin, that's within the XY plane here. You specify an angular location from the positive x-axis of that radius. So this is r, there's theta. And then from this point, you specify a third parameter, which gives the distance up or down. Okay? But what's interesting to think about is that regardless of what the coordinate system is, a direction is always the exact same concept, in that you can think of it purely as just an arrow pointing in some orientation. Like this, for example. This is a direction. You know, it's easy to look at an arrow and think, because it's straight like this, that it must be a direction associated with a rectangular coordinate system which has straight axes, but not like a cylindrical coordinate system which has curved axes. But no, not at all. Think about it. This is still just 3D space. It doesn't matter what the coordinate system is. You specify direction by, you point in that direction with your arm. It's an arrow. And furthermore, it's not like this direction arrow needs to have its tail at the origin. Think about it. You could be in a big room where the origin's like in the center of the room, but you can be standing anywhere in the room and you can specify a direction. You could be over here, specify this direction. Okay, and furthermore, what you can notice is that the length of the arrow doesn't matter. When it comes to a direction, it's strictly the orientation of the arrow and where the head of the arrow is. That's it. Okay, and now, but how would you specify a direction? What would be a way that you could specify an arrow like this? A direction arrow like this? Well, if you think about it, what you could do is, if we're thinking about a direction in 3D, all you need to do is just give 3 numbers. 1 number for each of the parameters of whatever the coordinate system is. So why would 3 numbers specify a direction? Well, for example, let's say we're working with the Cartesian coordinate system, and to specify a direction, you give the numbers 3, 5, minus 2. Well, what this means is that we could come to any point, anywhere in 3D space. It could be the origin, but it could be anywhere. Let's say we come to this point here. Now, starting at this point, what we do is we go 3 units parallel to the positive x direction. 1, 2, 3. 5 units parallel to the positive y direction. 1, 2, 3, 4, 5. And then 2 units parallel to the negative z direction. 1, 2. So that's something like that. And then we connect the start and end dots with a line, and then put the head of the arrow at the end dot. And there's the direction that you specified. And again, we could put this direction anywhere in 3D space, and it's still that same direction. Okay, but now notice, though, the length of the arrow could change, but as long as the orientation doesn't change, then it's still the same direction. And how would that happen? Well, that would happen if you just multiplied each of these numbers here by the same scalar. As long as it's not a negative scalar. If it was a negative scalar, then this would stay in the same orientation, but the head of the arrow would go on the other side. So As long as you multiplied each of these numbers by the same positive scalar, it would just change the length of this arrow, but not the direction. Okay, but we could do this same process with the polar coordinate system. So let me change colors here. You could specify 3 numbers. Let's say 2, and then an angle would be something like 30 degrees, so that's pi over 6 radians. Let's do negative. And then z would be maybe 3. Okay, so let me start at the origin just to make it easier to plot this, but you could start anywhere. So, okay, we're going to go negative 30 degrees in the xy plane, so that's about 45, so kind of around here. And then 3 radiuses, which, let's say this is like 5 radiuses, so somewhere around here. And then 3 units in the z up. 1, 2, 3. So you've got, this is about 3 radiuses. Let's say this is 5 radiuses, so about 3 radiuses here. That's 90. That's negative 90. That's negative 45. There's about negative 30. And then okay. Like that. So there you go. There's this direction in cylindrical coordinates, but you can move this wherever you want, and it's still the same direction. This is still the same exact direction. Okay, but you could specify a direction in 1 dimension or 2 dimensions. For 1 dimension, you just need to give a single real number, like 2. In the case of 1 dimension, there's only 2 possible directions, either, in the positive or negative direction. So the number 2 would be, you could start wherever you want. That's this direction. Or you give the number 1, it's the same direction. It's only when you have a negative number that you're specifying to the left. Okay, but in 2 dimensions, you would specify 2 parameters. So you could start here, and you've got negative 3, 1, 2, 3, negative 4, 1, 2, 3, 4. So there you go. Okay, but now how are there directions associated with things like price or revenue? You can have a price vector or revenue vector, cost vector. Okay, so where this is coming from is that, remember, what we learn in algebra is that in order to analyze relationships between variables, any variables in business, chemistry, biology, whatever, art, one of the tools that we use to do this is we use coordinate systems. We take this device that's fundamentally used to map points in 3D space, and we use it as a tool to analyze relationships between variables that don't necessarily have anything to do with 3D space at all. That's what graphs are. So for example, like what we do is we might want to analyze the relationship between the weight of a package and the volume of a package and the corresponding price or cost to ship that package. And so what we do is we get a bunch of data points. A package comes in. Okay, so here's like this system here. A package comes in. You've got these 2 input parameters here. I'll say X and Y. That's the weight and the space taken up by the package. And then the output is the cost to ship the package. And you just get a bunch of data points, maybe 50 of these, whatever. And what we do is we take a coordinate system, typically the Cartesian coordinate system. Here we have these 3 variables. So we're going to use a 3D Cartesian coordinate system. And the axes are scaled based on, so X would be the weight of the package. Well, each tick mark here along the X-axis would be 1 kilogram or 5 kilograms, whatever. Then you have the size of the package, like the space taken up. So maybe each of these tick marks would be a cubic meter or something. And then on the z-axis, the cost to ship the package, each of these tick marks would represent, $1 or something, $5. and we can plot all these data points. And maybe with enough data points, we could just connect those dots to get like a full graphical estimation based on any X and Y input, any weight and size input, not just strictly the data points that we collected. Okay, but what you can see here, though, is that this is where the idea of like a vector related to price or the weight of a package, the size of a package, these concepts that have nothing to actually do with 3D space, that's where this language comes from. That's how you can have a price vector. The price can go north, right? Or it goes in these directions. It's because we're using coordinate systems as a tool to analyze relationships between variables. That's the reason. Because I could make a direction here, right? Just specify three numbers, three parameters. So a weight of 5 kilograms, a size of 3 cubic meters, and a price of $10. And you can make a direction. 1, 2, 3, 4, 5. 1, 2, 3, and then you'd go up 10. So, somewhere up here. Okay, now the last thing I want to talk about is, I think this example here with the packages and the shipping weight really helps to illustrate the idea of these different dimensions, where these coordinate directions are like independent. You'll hear that a lot. These directions are independent. This X direction is independent from the Y direction and the Z direction. They're different dimensions. Okay, so one way of looking at independent, two terms being independent, is that you can't combine them. So we know from algebra, if we had something like 3x plus 2y, we can't simplify this anymore. We can't combine these two terms. They're independent, right? And it's the same idea here, in that if we have the weight of a package and its size and volume, those are like independent parameters. We're not going to combine add a weight to a volume of the package. It's two different variables, right? That's why they get plotted on their own separate axes, coordinate axes. They're independent. It's two different directions, two different dimensions. And same with the price here. And that's how you should think about vectors, in terms of vectors that related to 2 or 3 or multiple dimensions. It's these components that are independent of each other. However, they're independent, but they're still related, like they're siblings, in the sense that, so like you have these two inputs coming in here, this X and Y input. Well, those are in the system. They're coming in as a group. You need this weight and this size as inputs to get the output of the price, right? So they're coming in as a group here. It'd be like this two-dimensional vector coming in, and what's output is this single scalar output you could think about. In this case, it would probably be more like you input a vector in the XY plane here, the shipping weight, shipping volume. You pick a vector out of this plane, any vector, input that vector, and the output is a one-dimensional price value. Or maybe you could look at it in 3D space like this. The input is any vector in the XY plane here, and the output is on the Z-axis. But the idea is, even though you have these independent parameters, that they can still go together in a group, which we call a vector.